So thus far in this module, one of the things that we've dealt with is the kinematics of rotation. That is, how do we actually describe the way in which something rotates, which is not intended to predict how it rotates, but instead just being able to talk about what the quantities are associated with that. And we identified two quantities, angular velocity and angular acceleration. We've also sort of introduced an idea that's very analogous to linear motion, which has to do with conservation in rotation. And in particular, the idea that there is this thing called angular velocity or angular momentum, which is conserved. And torque, which is the flow of angular momentum, right? It's the interaction that causes angular momentum to change, right? And we've actually looked at for angular momentum this sort of idea that you can decompose angular momentum into a part that's due to the angular momentum of the motion of the center of mass. And then add to that a component that has to do with the idea that if an object is both moving and rotating, or translating and rotating, it also has a component of angular momentum that's due to rotation about the center of mass. Okay. And finally, we've introduced the idea that since torque tells you what the time rate of change of angular momentum is, or the flow of angular momentum, that you can write an equation of motion where if you look at some object, the sum of the torques acting on the object tells you what the time rate of change of the angular momentum is, in the same way that the sum of forces acting on an object tell you what the time rate of change of the linear momentum is. Okay. So we've sort of been developing these analogies between linear momentum and angular momentum, and at this point, we're now going to ask the question, how do we put this all together in order to actually describe the motion of objects that are both rotating and translating? And I'll note that in this video, I'm just want to talk briefly about the steps of that. Then in subsequent videos, we'll go through some examples of that. The steps for this are really very much the same steps that you did when we just were dealing with particle motion, right? The first thing that you do is you sort of think about it. And thinking about it involves both sort of thinking through what the keyframes are, right? Or what are the different sort of phases of motion, what's actually going on. So what's going to happen? Right? Use the fact that your brain is pretty good at actually intuitively thinking about what's actually going to happen in a situation. In addition to that, thinking about it also means thinking about what are the different interactions that are going to be present. Is friction going to be important? Is drag going to be important? Is gravity going to be important? And so forth. Okay? Once you've thought about it, then you go through the step of actually abstracting, which involves things like identify system boundaries and subsystem boundaries. And then once you've done that, that of course allows you to do things like draw a free body diagram, where you identify how these interactions interact with the system or with the pieces of the subsystem, and so forth. And this is sort of abstracting in a graphical sense, right? We're sort of deciding where the boundaries are, and we're deciding sort of how we're thinking about this object. Is it a rigid body? Is it a point mass? And so on. Or is it a collection of point masses or a collection of rigid bodies that are interacting? And then there's a kind of abstracting that's mathematical that we do. Which is to say that we have to decide on a coordinate system or set of coordinate systems that define the situation. In those coordinate systems, we need mathematical models for the forces and the torques. In those coordinate systems, we need expressions for the linear momentum and the angular momentum. And then finally, once we've actually got that mathematical abstraction done, then we apply conservation, which is we say, okay, well, we know what our mathematical models are for the forces and the torques. We know what our expressions in this coordinate system are for the angular momentum and the linear momentum of the different objects. Well, we're going to apply the fact that the sum of forces tells you what the time rate of change of the linear momentum is. The sum of torques tells you what the time rate of change of the angular momentum is, in order to get differential equations for the state variables. Right, so at the end of the day, you would actually like is, for example, some expression that says, theta double dot equals, some function of stuff, which would then allow you to either solve that differential equation analytically, look at what some of the limiting behaviors of it are, and also obviously be able to put it into MATLAB and make sort of simulation predictions about how the system's going to behave. Okay. So this is exactly the same type of thing that we were doing when we were dealing with point mass motion. The one sort of new piece of information is now we've got additional differential equations that we're going to be bringing to bear in the system, because we're not only looking at momentum being conserved, we're also looking at angular momentum being conserved. And in the examples, we'll walk through sort of how that plays out in some different systems.